Star. Hello, everyone. This is Benito Marcote from Jive, and I'm delighted to welcome you on behalf of the organizing committee of this fourth series of seminars sponsored by the European VLBI Network, focusing on high-resolution radio astronomy. So I would first like to start mentioning a few topics on the logistics before we begin with this seminar. First, you will all be muted throughout the presentation given by Mike this time. But then you are all invited to type in any questions that you may have for our speaker, preferably through the Q&A section at any time. Or if you are in the YouTube chat, you are welcome to put any questions that you may have there. And then after the talk, we will move to the question section right after the presentation. Please try to write your questions clearly and keep them short, please. You can also raise your hand if you want, so you can actually make the question yourself if you prefer so. We will aim to get as many of your questions as we can, but we apologize in advance if your question is not among those that we have time to answer. We will try to keep the seminar within 1 hour. Okay. And then now I will pass to Hannah Vatericid, who will now introduce today's speaker, Mike Garrett.
Hello, everyone. Thank you, Benito. It's my great pleasure to introduce Professor Michael Garrett, who was Wide Director of the Joint Institute for VLBI in Europe between 2003 and 2007. He developed the technique of wide-field, very long baseline interferometry and spearheaded the rollout of real-time VLBI across the European VLBI network and beyond. He was also instrumental in finalizing the original design concept for the SKA, and his scientific interest in astrophysics are eclectic. Next, Professor Garrett was General and Scientific Director of Astron between 2007 and 2016. He was responsible for the final design, construction, and operational phases of the International LOFAR telescope. Now, Mike is the Sir Bernard Lovell Chair of Astrophysics at the University of Manchester and Director of Jodrell Bank Centre for Astrophysics. Mike's main scientific focus is in searching for anomalies in large astronomical data sets, looking for the signature of energy-intensive extraterrestrial civilizations across the electromagnetic spectrum. He is chair of the International Academy of Astronautics SETI Committee and serves on the scientific advisory boards of both the SETI Institute and Breakthrough Listen. In 2024, he was elected as a Fellow of the Royal Society. Finally, let me mention that his PhD thesis was about gravitational lensing. Mike, the floor is yours.
Okay, thanks very much, Anna. I'll just share my screen.
Yeah, the sharing started. We see the presentation full screen, please. Okay.
You see that? Yep.
Yes, yes.
Okay. Well, thanks for the for the very nice introduction. So what I'm going to talk about today is SETI, Search for Extraterrestrial Intelligence, which I'm sure many of you know quite a lot about. Sometimes referred to as technosignatures these days. And in particular, I'm going to focus on the research that we've been doing in Manchester, which I think is a little bit different from sort of maybe the traditional SETI that you might be familiar with. So let's get started. Doesn't seem to be. Okay. So this question of are we alone? For me, this is really one of the big questions that any scientist can really wants to try and address, and it's a question that is not only of interest to scientists, but I think it's of interest to the general public. People really want to know the answer to this question. Is there sort of life beyond the Earth? Is there intelligent life? beyond the Earth? Are there sort of thinking, conscious beings like ourselves, elsewhere in the Milky Way galaxy or elsewhere in the universe? And so for certainly the last 5 years, most of my research has been focused on addressing this kind of really big question. So I didn't really set out to sort of build up a group in Manchester, but somehow it just seems to have happened. And our focus has, as I mentioned before, just trying to focus on things that haven't been done before, trying to just push the boundaries of SETI into sort of uncharted waters. And the other thing that I think kind of maybe we try and emphasize is that we really are coming from an astrophysical and an astronomy perspective. And I think maybe as you'll see as we go through the talk, it's really important that if you're going to identify, artificial signals in the midst of a lot of natural signals, a lot of astrophysical signals, that you really need to know the astronomy and astrophysics pretty well in order to be able to do that. So that's the other kind of direction that the group comes in. So I want to mention the people within the group because they've all contributed to what I'll discuss this afternoon. In particular, those on the left-hand side of this slide. We have 6 PhD students at the moment working, some totally on SETI, some half-time on SETI, and we also have on the right-hand side, we have the academic staff that are either interested in SETI or are actually supervising SETI research in Manchester. We also have one new PhD student who I can reveal to you today is Erica Rea. Some of you will know Erica. She worked at the SRT in Sardinia during the summer as part of the Breakthrough Listen internship scheme. So Erica is going to be joining us in 2025. And we're just about to put out an advert for a postdoctoral researcher hopefully in the coming month or so. So we'll be expanding the group actually over the next 6 months or so, which is great. So one of the reasons that I'm sort of involved in this game is because there's really been a rejuvenation in the field. There's huge interest in the field at the moment, and I think that's largely because of the Breakthrough Listen initiative, which I'm sure many of you are aware of. This is funded by the Breakthrough Foundation. It's funded for basically another 5 years at the moment. It has relocated from Berkeley in the United States to Oxford. At least that's where the main contract is now held. But it's really distributed across the world. So there's lots of activities in the US, in Europe, in South Africa, in Australia, China. SETI is happening everywhere, and I think Breakthrough has really been the initiative that's caused all of that, and we've also benefited from that in Manchester. I never set up to kind of build up this group, but somehow it's just happened by the fact that bringing on a master's student led to some PhD students, and now actually quite a substantial group that we have now. And this has actually been recognised quite recently. The activity in the UK, we're going to have a National Astronomy meeting, as we always have, in Durham in 2025, and there will actually be a SETI session at NAM 2025. So there's a lot of things happening in the UK, but I think you also see that that's also true in other European countries, in particular Italy, for example, Ireland, Sweden. So SETI at Manchester. So the sort of circles there are some, but not all, not everything that we do, but these are probably the main things that we are interested in the moment within the group. Unfortunately, I don't have time to talk about all of them. In particular, I won't talk about the things that you see on the left-hand side, but I will talk about the other 4 topics on the right-hand side. And we're not only doing research. The other thing that we're doing is we have this course which has been hugely successful. Started in 2018. Are we alone? But actually, it's not just addressing sort of the astrobiology of SETI and sort of SETI and sort of radio SETI, optical SETI, etc. It's also looking at the societal and the cultural aspect of the topic and this question. So very popular with students. It cuts across all faculties in Manchester. So I think this year we have about 150 students taking that course, and quite a few of them have actually gone on to do masters, and we have at least one at the moment who's doing a PhD in SETI. So I'm going to start with the topic of Earth leakage. I think it kind of introduces, the kind of signals that we are, looking for, that we are able to detect with the kind of technology that we have at the moment, the kind of, for example, radio telescope technology. The leakage radiation that the Earth produces, and trying to understand that, can give us an idea of the kind of things that we can detect ourselves. And so one thing that's interesting, of course, is that, if you are on a different star, or rather a different planet going around another star in the Milky Way, and you look back at Earth, then any leakage radiation that's there is going to be modulated by the fact that, the Earth has continents, and most of the leakage is coming from the continents rather than the ocean. So what you see in terms of Earth's leakage radiation really depends on your sort of line of sight towards the planet, whether you're looking from the North Pole or the South Pole, for example, but also the fact that the planet is rotating. So we've been trying to sort of simulate that also for a variety of perspectives. And I think we've already sort of more or less addressed the mobile towers and mobile communications, digital mobile systems that you see down there on the bottom left-hand side. And we have a paper out on that a few years ago. What we're also looking at is these other sources of radio emission, which are a bit more difficult to characterize. But we know that, for example, transport systems are using, even cars are using a lot of radar these days. The power grids and chargers, especially chargers that we see popping up everywhere, they're also producing quite a lot of radio frequency interference, if you like. So it's interesting. We hope at some point to try and characterize that. What we're working on at the moment is a kind of update on doing proper simulations of military and civilian radar systems and TV and radio transmitters. And the student who's working on this is Miro Saeed, and he was also the person that did the original mobile tower simulations. In the future, we also want to look at the growing number of satellites around the Earth. So these are how we sort of simulate the mobile towers. There are millions of these around the planet, millions of these transmitters, and they have this basic characteristic that they transmit in the sort of along the horizon, right? There's not much point of them sort of having any sensitivity to the sky, because most of the people that they're serving are down here on the surface of the planet. And that's quite interesting, because that means that basically you only really see the gain from these towers as they're rising, as you see down here, or as they're setting. To simulate it, obviously, you need to understand the positions of all these mobile towers. And in fact, there's a public domain database, which is almost certainly not complete. So actually, the situation is probably quite a bit different from that. There's probably a lot more towers than are presented and are part of the simulations. But nevertheless, it gives us a sort of good idea of the type of signal that we would see just from digital mobile tower infrastructure. And this is very similar to the work by Sullivan back in 1987 when they first tried to simulate the Earth's radio leakage. They didn't really simulate it; they just had some ideas about what it would look like. Of course, there were no mobile towers at all back in 1978 when they made the paper. So this is a new sort of contribution of leakage that wasn't there 40 years ago, and that's actually one of the reasons that we did this update, because at least the TV stations are probably very similar to what they were 40 years ago, but this is a completely new contribution. In the future, one of the things that we really want to do is look at satellite constellations. So as you know, it's predicted that there's going to be something like 100,000 satellites in orbit, low Earth orbit, by the end of the decade. We also have satellites in geosynchronous orbit. They're communicating with each other. They're communicating now with our mobile phones directly. They're communicating with downlink systems. There's uplink systems. So the Earth is really becoming, really a bit of a hot potato in terms of the radio emission that it's producing. I hear some people sort of, I don't know why they say it, that somehow we don't use radio waves as much as we used to, but we use the internet. Well, the only way the internet communicates, especially on mobile systems, is using Wi-Fi and radio waves. So actually, we're becoming much brighter in the radio than we've ever been before. I won't go through the kind of things that we plan to do in any detail, but there's a lot of interesting things we can do. We can look at the evolution in the past. We can try and predict the future, but that's actually really difficult over more than, say, 5 or 10 years. And we'd also like to do this across the electromagnetic spectrum and do it properly, not just kind of estimates, but actually do the simulations and have the fact that the Earth is rotating. And so Miro Said is working on that. Okay, so I want to move a little bit forward. That's the kind of background of the stuff we're looking for: narrowband radio signals, but also broadband radio signals, although that's probably more difficult to detect than narrowband signals. But Dysonian SETI is something that I, in particular, find really interesting, and I've been working on since for almost 10 years now. And this is the idea that if you're a technical civilization and you're an energy-intensive technical civilization, so you use a lot of energy. For example, on this planet, our energy demands are clearly increasing. And they're likely to probably increase quite a bit more than they have been in the past with the coming of artificial intelligence. It doesn't take long if you continue to, increase your, energy consumption by a few % each year, which is what we're doing at this moment. It doesn't become long before you exhaust, the energy that you have on the planet or incident on the planet. And you have to begin to sort of collect energy from the sun. The sun's a fantastically efficient source of energy, and you can just go out there and collect the energy and then reuse it for something else. But obviously, you have to have some sort of system that's collecting the energy, Dyson Sphere or Dyson swarms, whatever or bands, whatever you want to call them. But you have to collect that energy, and you'll probably reuse the energy. You simply have to get rid of the energy, otherwise you're going to melt. And so the spectral energy distribution of a star will change if you're extracting significant amounts of energy from it. And in particular, you have this bump in the mid-infrared that's basically just due to waste heat. I'm sure you're all familiar when you run your computer and you ask it to do a lot of work, then you'll feel the heat from that computer or from that laptop. Well, it's exactly the same. This is the the second law of thermodynamics that tells you that energy conversion is not perfectly efficient, and you always have waste heat whenever you change energy from one form to the next form. And that manifests itself as this bump in the near infrared, in the mid infrared, assuming that the work you're doing sort of has a waste heat of about 300 Kelvin, should be in the mid infrared. Well, a group of Swedish astronomers and SETI scientists actually looked at 5 million stars to see if they could see this bump in the spectral energy distribution of the stars. And they published their work about a year ago in monthly notices. And they called attention to 7 candidates that they thought showed this bump in the mid-infrared and could actually be promising Dyson Sphere candidates. So they didn't really go beyond that, but of course the press, especially the popular press, especially here in the UK, kind of went to town on that. And when we saw this, we thought, this looks really interesting. These are 2 of the 7 candidates that they identified, and you'll see this bump in the mid-infrared. These are observations made by the WISE spacecraft. It's a sort of a near-infrared, mid-infrared spacecraft that did a lot of interesting science. But they see this upturn in the spectral energy distribution, and this is exactly what you would expect from a Dyson Sphere. They also, I think, did a good job in looking at sort of possible contaminants, worrying about debris disks, for example. If you have a debris disk around a star, obviously that will radiate strongly in the mid-infrared and the far infrared even. So they looked at those, and they thought that they had really 7 good candidates, and they published those. So it seemed to me that, if these were Dyson Sphere candidates, then it would be interesting to see if they have any radio emission associated with them. And there are at least 2 reasons for this. The first reason is that if you're trying to manage the disposal of heat in these Dyson Sphere systems, then one way you can do that is that you can emit coherent low frequency radiation in the radio domain. At least that's one of the theories that's predicted. So I asked Tong Tian if he would go and have a look and see if there was anything in the radio surveys that suggested there might be a radio association with these 7 candidates. And he came back and had found that 3 of the candidates had radio emission. Now I should say that these are sort of M-dwarf stars, so the most abundant stars in the galaxy, certainly in our region of the galaxy. And for these 3 out of the 7 to have radio emission, that's really a bit fishy. And being a skeptic, of course, I didn't think that this was going to be a SETI signal. So that I immediately thought that very likely there's actually contamination in these systems, and that what we're looking at is not just a star, but some kind of contaminant. And the obvious one, when you have radio emission, the obvious one is that there's some kind of background galaxy that's also contributing to the measurements that WISE has made in the surveys. So these are just the positions of the radio sources. You can see these on the candidate A and B. They have detections from the ASCAP surveys, and this source, which is actually quite bright, and is the source that we followed up, is in many different radio surveys. So we decided that we'd have a look at candidate G, partly because it was much brighter than the others, and also because it was quite a bit further north, and so we could see it pretty well with e-MERLIN and the EVN. So we made these observations in the summer of 2024. We'd just like to thank everyone, e-MERLIN and EVN, that made this possible. Did a great job in getting us the very good data, and also pipelined the data. So this is, you see here we have the e-MERLIN map. Just like to thank David who processed this data for us. You can see the structure there. So, it's kind of obvious that this is some kind of AGN system just from the morphology of the system. And then we got EVLBI data. I love EVLBI, not because I was part of the team that kind of rolled it out, but actually because I'm just really impatient for data. I just can't wait for data. If I've got an idea, I want the data right away. And sort of EVLBI, well, gets you as close to that as you probably get in not just VLBI, but in radio astronomy. So yeah, I really advertise EVLBI. I think it's a great thing. We should be doing more of it. But in any case, the central object here in the detected by e-MERLIN is also detected by EVLBI, and thanks to Benito for also pipelining the data. We were able to detect this through phase referencing really easily. It's really a standout detection. It's about 10 millijanskis or so in the peak. And well, essentially everything it's telling us, including the VLBI result, brightness temperature, way beyond 10 to the 6 Kelvin. This radio source is an AGN. And probably the other radio sources that were associated with the other two Dyson spheres, they're probably also background AGN. But it's a bit more complicated than, just contamination, because you would see that, if you looked at an optical image, you would see that there's a galaxy there and there's an M dwarf and they're close to each other. You have to sort of think that this galaxy can't be a normal galaxy. It can't be obviously there in the optical. So the only way it can be a galaxy and not there in the optical is if it's really dust obscured. So you have these hot dog galaxies that are really quite bright in the mid-infrared, but are really very faint, in fact undetectable in the optical. And so this is the kind of scenario we have for candidate G, but also at least two of the other candidates. Y is, of course, it has a small aperture, so especially in the mid-infrared, the beam is actually quite large, so it definitely encompasses both the galaxy and the star at the same time, especially in W3 and in the W4 bands, the mid-infrared bands. And although, at optical wavelengths, this galaxy is really faint, much fainter than is depicted here in this cartoon that I made. But as you move into the near infrared, it begins to get a bit brighter, probably detectable in the near infrared with something like JWST, for example. And then when you get into the mid-infrared, when you get into Y's, W3 and W4 bands, it's really the dominant contributor to the flux density at these in the mid-infrared. So what was I going to say? So the other interesting thing about this, of course, is that the other confirmation of this is that you see a shift in the centroid of the mid-infrared emission. It moves from the position where we know the M dwarf star is. We know that really well because of Gaia, to the position that we know really well from the radio and from e-MERLIN and from VLBI. In W1, the star, so in the near infrared, the star is totally dominating the emission. But by the time you get to W3 and W4, the galaxy is dominating the emission. And this is what you see here. So you see the star here. This is the Gaia position for the star. This is the radio position for the galaxy. So in W2, roughly in the near infrared, the star is dominating the emission. And then as you move to W3, you can see the emission just shift over to the position of the galaxy. So is this kind of plausible? Do hot dogs, have the number aerial density on the sky to do this? Well, we think that they do. They are extremely rare. So you have to look at a lot of WISE sources to be able to pick up one of these. But especially because of the size of the beam that WISE has, there's a good chance that you'll get contamination. If you look at 5 million stars in the Milky Way, there's a good chance that you'll see something in the background for a handful of those 5 million. We think that that's probably what's happening here. Although, I mean, personally, I really hope that those other 4 Dyson Sphere candidates really are Dyson Sphere candidates, and maybe we've just been part of the process of eliminating 3. But if I was to put a bet on it, I would say that, you know, probably all 7 of them are suffering from some kind of background contamination, and possibly even contamination from debris disks around the star. And I think this result, we really like this result, because I think it comes back to this point I was trying to make earlier, that what we're trying to do in the group is really bring an astronomical and astrophysics perspective to the problem of SETI. And really to be able to detect, you know, artificial things, you really need to know about the natural things really well as well to be able to do that. And so I think that's what this shows. Wouldn't be a SETI talk if I didn't have a Carl Sagan quote in it. So here is the famous one, which I think is a good one, especially for SETI. Extraordinary claims require extraordinary evidence. Okay, so moving on, I want to say a little bit about SETI interferometry. I think interferometry has I think at the moment, most SETI is being done by single dishes. We're kind of moving towards beamformed arrays. But I personally think, and I passionately think, that, you know, if you've got an array, you should be doing interferometry with it. And I think there are some reasons why there are advantages to doing that with SETI. Again, this is work that Kelvin Wandia did for his master's thesis. Kelvin's still part of the group. They're mostly looking at radio stars at the moment. Builds on stuff that I did, and Hayden Ramparadath also did. If you remember, Hayden was in Jive in Leiden and Manchester and did his PhD in Australia. So he also contributed to doing SETI with VLBI. There are a lot of reasons why this is a good thing to do. Using interferometers, looking for SETI signals. You know, first of all, we have the advantage that you know, because the fringe rate is so high, you know, fringe rate depends on the baseline length, but it also depends on, you know, the position of the source of RFI. If it's far away from the phase center, then you get a very fast fringe rate, which means that the signal decorrelates for signals that are outside the field of view. You know, it doesn't work perfectly because, of course, we still have compression of the front ends of receivers and other artifacts that RFI brings, but it's much better than the situation you have with a single dish. For example, there's a significant reduction in the amount of interference in the data, especially when you have really good spectral resolution. This is also one of the things people don't really understand, because VLBI doesn't really have great spectral resolution, but when you have really good spectral resolution, which is what you need for SETI, you also have a lot of clean space there, apart from all the caveats I mentioned. So the other thing I really like about the interferometry approach is that you have sort of multiple independent detections on each arm of the interferometer. That's obviously a good thing, especially if you've got some kind of transient event that isn't going to repeat, then you really know that you've detected something. And then the other thing is, of course, that with SETI, and I haven't really explained this very well, but with SETI, everything is kind of changing. Everything's changing under your feet. In particular, if you're looking at sort of very narrow band signals, then because there's relative motion between the transmitter and us, the receiver, that relative motion gives you sort of a Doppler shift in the data, and the motion is changing all the time. So that there's a Doppler, so-called Doppler drift in the data. So the signal's never where it was. It's always moving and changing, and can quickly change from one channel to another channel in a matter of 10 seconds or so. So the only thing that's really invariant in a SETI experiment, and this is only true for objects that are distant, so interstellar distances, is that the position on the sky shouldn't change. So this is actually quite important, and of course VLBI gives you fantastic positional information, but that shouldn't change. And of course, as we've seen with the work that people like Jolt and Benito have been doing in FRBs, being able to pinpoint the location of a signal or an FRB tells you an awful lot about the characteristics of that signal. What kind of environment does it sit in? Is it associated with a star, or is it slightly offset from a star, maybe a planet, or is it free flying? Because you can also measure the motion of a SETI signal in principle if there's one out there. If it's on a planet like our own and an orbit of 1 astronomical unit, and it's an orbital motion around its star, then that's something that's certainly easily detectable over a year, that orbital motion. And maybe more likely these signals are going to be on free flyers of some sort. Then again, if they're going really fast, you can detect them in maybe 12 hours, 24 hours. If they're going slow, like some of the spacecraft that we have going out of the solar system at the moment, like the Voyager spacecraft and New Horizons, then you can also detect them over timescales of a year or so. So if there is a SETI detection, VLBI is going to be really important in trying to understand the characteristics of the radio source. So we've been over the last few years, we've been sort of getting data, mostly not really doing science with it, but mostly trying to understand the technicalities of how we should be doing sort of VLBI and SETI VLBI. And so this is the stuff that Kelvin did for his master's thesis. Basically, we had this nice rocky planet that's sort of right next to a VLBI calibrator. So you can observe both of them, they're both within the field of view. And so we were able to calibrate all the data on the calibrator and then transfer that to exactly to the position of the star, and then look for any narrowband signals. And so we learned quite a lot from this experiment because we detected exactly what we were looking for. We detected a narrowband signal that was persistent and was detected on all baselines. And this is only a few channels. Well, no, that's not true. It's many channels wide, so it's about 1 megahertz, and it has structure within it. But the only thing it doesn't have is the Doppler drift that I mentioned before. It's totally static in frequency. So we were pretty, although we were excited by this, we knew that this wasn't a SETI signal, from the get-go, as it were. But we also wanted to try and understand what this signal was. It was exactly where we expect to see 21 centimeter hydrogen, but you don't expect the 21 centimeter line to have a brightness temperature that's detected on the long baselines of VLBI. That's for sure. So what could this be? Well, this is the picture I took of Kelvin when we talked to an awful lot of people about this. Probably some of them are on this seminar about what it could be. And the thing we hadn't really realized was that the Kepler field, and I should have known this because it's in Cygnus on the sky, that it's actually really within the galactic plane. It's only 5 degrees above the galactic plane. So you're looking through a lot of H1 when you make these, when we were making this observation of the planet. So this just shows you this weird kind of signal that we see around the H1 line, and it also has the more or less the structure of H1 that you see with a single dish. So what's happening here is that what you'll see here that the brightness temperature of hydrogen for a single dish is about 80 Kelvin. So it's several times the noise temperature of the receiver. So it's actually a really big signal if you're looking through the galactic plane. And although it's only confined to a few channels, the thing is that when you cross-correlate one noisy baseline with another noisy baseline, and the noise is created from a common source, you're going to get a correlation in the data. And that's what we see here. And you would never normally see this in normal VLBI, even in spectral line VLBI. You'll never see this. No one's ever reported this before. It has been seen in the VLA before, when the VLA was just starting up. But you only see this because we've been using 500 hertz resolution in this experiment. And that's the thing I like about this SETI stuff, is that because you're pushing things to extremes in all sorts of dimensions of parameter space, you discover stuff that you didn't know. This is in every VLBI data set, in a sense. But it's just that if you don't have this kind of spectral resolution, you'll never see it. So we realize this is just an artifact of the noise properties due to hydrogen being in the beam. And we verified that because we also got some time to look out of the plane of the galaxy. So this is 3C345, exactly the same experiment. We detected the Kepler H1 artifact emission, but when we go out of the plane, we don't see anything. And again, this is because when you're looking out of the plane, the brightness temperature here is only 2 Kelvin, so it's a tiny fraction or a small fraction of the noise properties of the receiver on your telescope on your single dish. So we learned a lot from that, and we're still learning, and we're very excited. On Friday, we have this ORP multi-telescope project. Evan Keane and myself are the PIs. We're going to be doing simultaneous SETI on an interesting target with iLOFAR, Swedish LOFAR, e-MERLIN, the EVN, the SRT. I'm not sure if it's 5 gigahertz or maybe 26 gigahertz, I think it is. And we hope to also rope in the ALMA telescope array around about 5 gigahertz or 10 gigahertz. So we're excited to do this because I don't think anyone's really done a proper job of doing SETI simultaneously across such a wide band of frequency. So that's happening on Friday. We already have observations in the can, so to speak, of spacecraft around Mars. And particularly, we'd like to use the PRIDE data analysis software that Jive has been building up over the years to do the spacecraft navigation and spacecraft tracking, because that's exactly what you need in order to be able to do SETI. So at some point, we hope to get that back correlated and to have a look at the data. I'm sure that will be a project of one of our PhD students. And then the other thing that just kind of came up, we just submitted a proposal to try and get triggered observations. In the case that there's a breakthrough listen candidate, breakthrough is now looking, at 1 million stars with Meerkat, 1 million stars with the VLA Cosmos backend. There's going to be a lot of candidates coming up in the near future, just like breakthrough listen candidate 1. And we don't want to leave these just to the VLBA or to the LBA in the southern hemisphere. The EVN and e-MERLIN should be doing something here as well. So we hope that we'll have the ability to also respond really quickly to these kind of interesting candidate events. So still on the topic of interferometry, but I want to shift up to higher frequencies. So this is a plot that you've probably seen a few times, and even SETI people show this plot, which shows the millimeter and the submillimeter to be opaque. Of course, it isn't opaque. If you go high enough, then you have these transparent bands where you can do astronomy, and ALMA does that really, really well. And so we got our hands on some archive ALMA data. And the reason we do this is, well, I think there are a lot of advantages to going to higher frequencies, which I'll go through really quickly. Now, first of all, the RFI environment is much, much better. All the propagation effects goes frequency squared. So, 100 gigahertz compared to 1 gigahertz, nothing really bothers you at some level. It opens up a completely new window on the technosignature universe. And of course, ALMA is a fantastic instrument. It's got great sensitivity, fantastic spatial resolution. There's some disadvantages as well. This drift rate that I spoke about before is proportional to frequency, so it becomes really large, 100 times larger than we have in normal SETI experiments. The sky, the spectral sky, is quite, more complex than we have at centimeter wavelengths, so that may be an issue if you're looking towards the galactic center. But I think if you're looking out of the plane, we've seen that this is not actually an issue. And of course, the field of view is more limited. So Lisa Mason has been working on this, and she was looking, she found the data, very high spectral resolution data for ALMA. This is the highest resolution data that's in the archive. We have the whole field of view is accessible to us from time smearing and bandwidth smearing with ALMA. That's a really nice feature of the array as well. So you can look at all the Gaia stars that have distances in the field of view, and you can sort of, go through all the frequency channels looking for a narrowband signal. And so that's what Lisa did. We didn't find any, which is unfortunate, but it's just the start on what I think is really important. So Lisa has published this paper in Monthly Notices, just came out in 2024. I do want to, just as I'm wrapping up, these are the last few slides. I hope that's given you a flavour of what we're doing in Manchester, but I think SETI is a much deeper and bigger question, and especially these days. I don't know how you feel, but I feel a bit worried about where we're going at the moment, as a civilization. And SETI sometimes makes us think about these things and ask questions of our own society. I'm not going to show the Drake equation, but this is kind of the reduced Drake equation. If you're incredibly optimistic about all the factors in the Drake equation, then basically the number of civilizations scales with the longevity of a civilization. N equals L. And that means, if a civilization like ourselves or whatever comes after us, if we can survive for, 1 million years, then SETI should be relatively easy. There should be lots of civilizations out there, even just like our own, 21st century civilizations that we can detect. But if we're down here, if a civilization actually only lasts for a few hundred years, then SETI is going to be hard, because the chances of us intercepting a signal at the right time and the right place and the right frequency, that's going to be difficult. That makes me think of this quote that I like from Arthur C. Clarke. Either we are alone in the universe or we are not, and both are equally terrifying. And I get exactly what he means from this. It's obviously a bit scary if there are other beings, thinking beings out there that have grown up in a different environment but are, intelligent. What will they be like? That's really interesting, but also a little bit terrifying. And maybe just as equally terrifying as this idea that, we're actually alone in the Milky Way or even in the universe, that there's no other thinking, conscious beings. That's also terrifying. And I think, especially given what's happening these days, it makes us think about certainly sustainability of our own planet, but also looking after each other. We share this planet, not just with our friends and families, but with almost 10 billion other people. It's a fantastic spaceship that goes around the sun every year, goes around the center of the Milky Way every 250 million years, roughly. And it treats us very well. And everyone has a right to be on this planet and to prosper on this planet and to share the fantastic planet that we have. And if we want to, go beyond this 100 or 200 years longevity of a civilization, then I think we probably have to change the way we do things. And so I will leave you with that thought and a summary of what I've talked about today. And thank you very much.
Thank you very much, Mike. Great presentation. Really, yeah, great talk about SETI and great summary. So, inside that, now it's time for every question. If everyone has comments or so, I will remind that you are welcome to write your questions in the Q&A section in YouTube chat, or raise your hand if you want to do it in person. We already have one question from the YouTube chat, and it's related to the part that you were talking about, the Dyson spheres. So in this one, you basically were saying what kind of signal we expect if that such structures are in some planets. However, the question is like there, you are assuming that any civilization is using the same technology for harvesting energy as the ones that we have or we expect here. So what happens if the technology is so efficient that, for example, they leaks no infrared emission? Would you still be able to reveal the existence of these Dyson spheres?
So I think it's a really good point, and I think I've kind of written about this last year, is that we can only really detect things that we have the tech, that we've developed technology for. We can only really detect ourselves or civilizations like ourselves at the moment, in a sense, or powerful radio beacons, because we don't have technology that maybe people are communicating with, I don't know, neutrino beams or gravitational waves or whatever it is, but we can't do that, right? We don't know how to transmit those signals at the moment. So we're kind of confined to our own understanding and our own capabilities in technology in terms of what we can detect. And that's why we do so much radio. I mean, people ask, why do we do so much radio? Well, it's because it's a thing that we can actually do best, especially in terms of frequency resolution. And the point about advanced civilizations, could advanced civilizations kind of cloak themselves? Could they actually reduce that waste heat signature? Well, yeah, I'm not going to try and judge what an advanced civilization can do, but as soon as they try and do that, it actually costs a lot of effort to do that. If you're trying to radiate stuff, at low levels, and for example, radiate it out, maybe not in the mid-infrared, but in the far infrared or whatever, you need really large radiators to be able to do that. So it costs a lot in terms of material resources. It's really difficult to get around the second law of thermodynamics. But at the same time, there's an awful lot of physics still to be understood. So I wouldn't rule out the chance that, we're just not bright enough, and that maybe really advanced civilizations can, have some tricks up their sleeves that make them difficult to detect. But at least from the physics we know, that's a really difficult and expensive thing to do. But it could be happening. So I sort of agree with the question there.
Maybe one quick comment before going to the second question. As you mentioned now in this answer about the frequency resolution, in the talk you mentioned that it's sometimes the limitation of VLBI observations that they have less as compared to the standard SETI searchers. But actually you can use it also on the reverse way. Like things in VLBI in general, you have access to the baseband data that is not possible in most of the ready observations. So actually you may actually go through much higher frequency resolution than in normal observations.
Yeah, and that's what we'd like to do with getting access to the Pride software, is to be able to work on the baseband data and to get whatever resolution you want. In fact, so if there was a SETI signal today, I think that's what we'd be doing. If there was a real SETI detection and we went off to do VLBI, what you're talking about is exactly how we would do it at the moment. We'd calibrate on the software correlator, and then we'd take the data into a correlator that can give you kind of infinite resolution. So it can be done. It's just that we haven't done it yet, and we need to start practicing how we do it so that we can do it if it ever happens.
Well, that's interesting to hear and actually good for the future. We have a question from Mario Basilicata. The question is, what's the typical range of distances in the galaxy that we can probe by searching for planets emitting radio waves? Because of course, the farther, it decreases by square of the distance. So with our current sensitivity, how far we can actually go?
So the leakage radiation, what we produce at the moment, is going to be really difficult to detect beyond roughly a light year or a few light years at the moment. And I'm really talking about the background stuff. There are particular things that happen occasionally that are bright enough to detect across the Milky Way, roughly. So, for example, extremely bright ionospheric radar systems that Arecibo had. That was the kind of signal that you can detect across interstellar distances without any problem. And also we have extremely powerful military radar systems that are also being used quite often, but they have a relatively low duty cycle. And they're certainly very directive, so you'd be lucky to pick them up. So we are producing a lot of bright signals occasionally that basically you can detect on interstellar distances, kiloparsec distances, and then on the Earth we have many more less powerful systems like mobile towers, for example, and even mobile devices that give you this kind of broadband background that's more or less covering all frequency spaces in centimeter wavelengths at some level. That's much harder to detect because the power levels are much less. But they do have the advantage, and this is something that I'm kind of interested in, they do have the advantage is that they really are kind of broadband. We're moving from 4G to 5G to 6G, and I know this is terrible for astronomy, but if other civilizations are doing the same, and they probably are if they're at our level of technology and not much more advanced, they're probably doing the same thing. So you have a lot of broadband things. So you can average, you can look for a continuum detection. But even here, the Earth is really difficult to detect, as a continuum broadband source. No, it's not impossible, but it's going to be really, really difficult. What you would hope is that much more advanced civilizations are using, somehow, if they use a lot more energy, then they also produce a lot more radio waves, right? That there's some scaling relationship between these things. In that case, it's possible that you might be able to detect this kind of mundane background radiation, not from planets that host civilizations like ourselves, but planets that host civilizations that are, for example, maybe type 1 or type 1.5, type 2, Kardashev type 2 civilizations, that there might be enough just, background emission coming from all the stuff that they're doing. Those might be detectable, but something like the Earth, we're not even a Kardashev type 1 civilization. That's not going to be detectable on any not on interstellar distances.
So how many, roughly, a few light years? They are kind of handful.
A few light years. Airport radars, for example, are, with the SKA, I think the canonical number is a few tens of light years. It really depends on what you assume, especially for integration time on these. SETI doesn't integrate. That's another thing that needs to change. SETI observations, you never hear about long integrations. So that 5 minutes is kind of standard, whereas I think what you can do with interferometry is you can begin to think about doing much longer integration times. Might be interesting.
Okay, one last question actually before concluding here from Matthias Cutler. If you will have sufficient resources and the political will, of course, which frequency would you transmit a message in order to make it convenient for our ET neighbors to detect it?
Yeah, that's a great question. and you put the water hole there, you know, and a lot of this is trying to find the place where we think people will transmit. And there's pros and cons to whether people, you know, other people, other civilizations would transmit on the water hole. My personal feeling is that centimeter wavelength SETI is, I'm not going to say it's run its course. It certainly hasn't run its course, but that we should be moving to higher frequencies. And I know Matthias is working on getting NGVLA systems here in Europe, and I think that's a really important thing to be doing, especially if we can do SETI on them. That would be really cool. But we need to be moving to this kind of above 20 gigahertz, I think, because it's pretty clear that on a planet, a lot of the communication is happening below 20 gigahertz, just because you're working within a sort of terrestrial atmosphere with a lot of water vapor in it. And at least biological civilizations are probably doing the same kind of thing. They're probably living on planets that have a lot of water vapor on them. But as soon as you get above, the atmosphere, as soon as you're spacefaring, then a lot of your communication, you don't really care whether, you don't care if it's below 20 gigahertz. You can actually go, work up to a terahertz, for example, with actually a lot of advantages, as I mentioned before. So my personal feeling is that going to much higher frequencies than we use at the moment is maybe the thing that could be a game changer for SETI. We don't know for sure, but it's certainly somewhere we should be looking at. And I think NGVLA, and hopefully if we have some antennas here in Europe, that would be a great system to begin to to do these kind of million star surveys, not at 1 gigahertz, but 100 gigahertz or somewhere around there.
Okay, thanks for the answers. I will finish just with actually a comment. It's not a question from Simon Carrington. That actually is a really good note. That is like all the experiments, developments that you are conducting here, because most of it requires non-standard setups, like including, as you mentioned, SETI, bright, precise, radar, etc. All of them actually are advantages that comes back to VLBI or interferometry in general. And actually, at the end, all of them together, they are pushing for new abilities that actually it can be accessible for the rest of the community if they're being tested here. So actually, that's a very good comment that it's not only SETI applications, but actually it will go back. It goes back to the whole community.
I mean, I very much agree with that, and I think the EVN actually makes itself accessible to be able to do these things. That's one of the strengths that we have in the EVN, is that we're not just purely sort of astronomical, that we're also trying to push the technique in different directions, and we give groups the opportunity to push things to new and different ways, and eventually that comes back and actually enriches the sort of mainstream astronomy that we do. And it's one of the features of the EVN that we should be proud of, and one of the things that we seek to preserve over the coming years.
And that drives back to the technology used there, actually. So it's 7 applications plus the technology.
Yeah.
So with that, we will finish here. I just have a very quick announcement. So we don't have fixed dates for the following seminar. The only thing I will briefly mention is that we have the JIVE VLBI school that will happen in September. And this will be a fully hybrid school for people that wants to learn how to analyze the VLBI data, or VLBI in general. And we will conduct the school here at JIVE in the Netherlands as main venue. We will have as auxiliary venue, synchronized and completely like in both sides at the University of Pretoria, plus an online mode there. So we are aiming to send the second announcements with the registration call in the following couple of weeks, hopefully. So you will hear about this, and please register and share it to students, especially early careers, people that wants to join and learn VLBI. And with this, I would like to thank you, Mike, for the great seminar. And thank you, everyone, for participating and joining the seminar. See you next time.
Thanks, it was a pleasure. Pleasure.